negative is different. So that could be a mistake. Okay, are there any two slopes up there that are opposite sign and reciprocals? This one and this one?
Yeah.
They're reciprocals and opposite signs. So what's that mean? KL is perpendicular to KM. So think where they would come together. KL, KM would meet at point K. So where's the right angle? Angle K. Would be the right angle. Now we didn't even look at a picture of that. If I would just real quick graph -2, 4, so K was like up here, 2, 1, there's L, and then 1, 8, M is up here. So this is a quick picture, evidently that is a right angle right there.
How come on LM you have a sloping negative?
I have -7, should it be -7 or +7?
7 over -1.
Should be negative, okay. They were telling me that it was 7, and I
It's
knew that there
7
was,
over
it's -7. 7 over -1, so that's -7. All right, thank you. And looking at the picture, it does go down to the right. Right. Okay, questions on that one? Okay, then I made up 4 different types of equations to write. And I thought these were basically the 4 that you're kind of struggling with. Okay, when you're writing the equations, what I'm telling you to do, and I checked with Mr. Bracy, he said this is the way that he taught you, start with point slope form all the time. No matter if it says put it in slope intercept, just start with point slope. And then if you need to, if you're to number 3, I wanted you to write the equation of the line perpendicular to the one I gave you. Now I gave you the equation this time in a nicer form, but I do want you to write the equation of a line perpendicular to it. So think about what's the relationship for slope of perpendiculars. So decide if this slope is 3, what slope you should be using to make it perpendicular. The last one is a perpendicular bisector. I talked with you a little bit about what point we would need to go. I don't, what's this one? No, I think we did divide by 2.
Oh, yeah, my bad. So it'd be
Okay, ready for our answers?
I'm still on number 3.
Yep. Right.
Yes.
The thingies and the thingies, I don't know how to answer that.
Oh, it's yeah, I did it right.
But to be perpendicular, you know, is where you're doing it. Number 2, you would say the same thing, but for perpendicular, you have to change the slope to opposite sign and reciprocal. Yes. Okay, so looking at those, let's see what we need to talk about. Okay, now on number 4, do you, okay, perpendicular bisector, we kind of talked about up here. Okay, you need it to go through the midpoint. You can't have the perpendicular bisector go through one end. So that's where you have to calculate the midpoint. Other questions? Are you taking good notes so that you can look this over in the next couple days and do better on that? This is my student teacher. He's usually not in here this time. wants to vote.
Don't mind the cripple.
Yeah. Okay, so questions, which one do I need to talk about some more for you? Yes, Jaden. Number 4, okay, what point did it have to go through? Did you find the midpoint? Okay, midpoint is where you average the x's and the y's. So -5 plus -3 and divide by 2, and then 0 and 6 added and divide by 2. So that should have been -4, 3. That's the point you needed to go through because we're doing on this one the perpendicular bisector. So you gotta come up with that midpoint location. Now the slope, realize you didn't keep the same slope. You had to change it for the perpendicular. So your original slope was 6 minus 0 over -3 minus -5. 6 over 2. So 3 was the original slope. Now I don't like to see on your paper, and I probably scribbled it out on your quiz or work, I don't want you to say equals -1/3, because that's not true. 3 doesn't equal -1/3. But what are we thinking on the -1/3? Well, to make it a perpendicular, the slope needs to be -1/3. So here's your slope to use. Notice it in the equation. Here's your x1, y1 to use in the equation, so that's where I got my answer. Perpendicular bisector. Did anyone get all 4 of them done correctly? We got a few people that way? Yeah. Good. Just need to get more and more of those. Right, before I leave that, any special question? Okay, let's go on to our actual lesson today. And that is to finish up section 4, I think it is. So in your notes, find section 3-4. I know we did part of it already, but the very bottom of the first page and the back side of it, we have some more things to finish up. And you will need compass and straight edge, so if you don't have any at your desk, this might be a good time to get up and get supplies if you need. I don't know if I need to get more out or not.
You're welcome, Jaden. No, I always. Going over here. Find us a ruler. Oh, I'm sorry, Jaden. I'm ready to play.
Seriously? Seriously?
Thanks, Colby. I guess that's fair.
Is there enough or did we run out? Come over here.
You're welcome, Jaden. Just have a seat.
Hey, put together a new packet here, guys. I think people probably took them home.
I mean, I have one in my locker, but I mean, I forgot it.
Well, that's why we're running out. Okay, take a bag, a compass, a protractor, maybe grab them and then
This is pretty neat.
that means grab one of each and those things.
Yeah, I was trying not to. Did you guys have a motion? Remember.
Right on your notes, in this section, we did already talk about perpendicular bisector. And I think writing the equation, if you think back to what the definition is, that should help you remember you have to get the midpoint, perpendicular bisector. Everybody's got supplies? All right, now, did we do the constructions of perpendicular bisector? You got that accomplished? Okay. And you did some graphing on your worksheet. So we should be at this point, it sounds like. At the bottom of that first page, there's a definition about distance from a point to a line. That's where we will start. Okay, the shortest segment from a point to a line is perpendicular to that line. So we're going to use that fact when we define what we mean by the distance from a point to a line. Because if I would give you this drawing and have you measure, I would guess some might say, okay, I'll measure from here to here. That's how far that point is from the line. Someone could measure to this end. Someone might measure to that end. Someone might choose somewhere in between here. Can you see all the various possibilities that someone might use to measure the distance from a point to the line? We need to agree on which one is the correct one that we're all going to use. Okay, and the distance is the length of the perpendicular segment from the point to the line. So from this point, perpendicular, I'm going to estimate is probably that one right there. So the distance from the point to the line is measured along the perpendicular, not just any point that you want. The perpendicular gives us the shortest distance from the point to the line. So in your definition there, a diagram, you might want to just draw the perpendicular. Perpendicular from the point to the line, that's the shortest distance, that's the distance we will always be looking at. Has to be perpendicular. So on your picture, you estimate where the 90-degree angle is. Mark it so you know what you were thinking. Now, some problems related to that. Here's how they'll ask some questions related to that. It says, name the shortest segment from point A to line BC. Okay, so from A, so it has to go from this point, has to go to line BC and be the shortest segment. So which one's the shortest segment in the diagram? Segment AP, correct. Shortest because it's along the perpendicular. Okay. Then they'll ask, write and solve an inequality for x. What do we mean by an inequality? What's an equality? What kind of math symbol's in an equality? Oh, come on. An equal sign. So if they're not equal, that means one thing's bigger or smaller. So what kind of math symbols do we put? What's that mean? Okay. Less thans or greater thans. We're not going to stick with crocodile. We're older than that now. Okay, so write and solve an inequality for x. So what do they mean? Well, x is over here. So I could say x minus 8, is it greater than or less than something else in the picture? Think about the shortest distance is along the perpendicular. So x minus 8 would be greater than 12. That's an inequality for x. Now if I solve it, solving inequalities is almost like solving equations. What do you have to be careful of? There's a time, actually 2 times, when you have to reverse that inequality symbol around. By or multiply by a negative. Multiplying or dividing by a negative reverses the inequality relationship. So this would be a correct answer. Someone might say, well, 12 is less than x minus 8, which is true. 12 is smaller than the x minus 8 because it's the shortest distance. Add 8, 20 is less than x. Remember the rule about put the variable on the left? Now when you put the variable on the left, the x still needs to be the big part. The 20 has to be the little part. So it would reverse to be x is greater than 20. Same solution, starting with a different inequality. That's the type of problem related to that definition. So let's try a second one for you to practice on your own. Come on. Change the picture and have you do the problem. Oops. Name the shortest segment from point A to BC and then write and solve an inequality for x. Picture is a little bit different than last time. The point is A, so it has to go from A. Which one is the shortest segment? Riley, shortest segment was,
12.
Nope.
Or AC.
AC is not shortest. Shortest is along the perpendicular. So go from A, which one's the perpendicular segment, Gretchen? AB. It's longer if you go on AC than AB because of the perpendicular. So now what's your inequality? Cody, what'd you do? A less than or a greater than. Did you get that first part right, Cody?
Yeah.
Okay, so you're saying AB is the shortest?
Yeah.
So inequality, AB is shorter than
AC.
AC. So x minus 5 is less than 12. So I think that's what I did. X minus 5 is less than 12. That's your inequality, or at least one version. Solving it, do what to solve it? Add 5 to technically both sides. So yes, we do get a 17. So x is less than 17 would be solving the inequality. Okay. It says, yes, write and solve it. So writing it is relating which one's larger, which is smaller. Question on that one? Riley, you see why the other one was the shortest segment? From A, the shortest segment is going along the perpendicular instead of going. It's like if I were standing here and said, how far am I from the front wall? Well, the shortest distance from me to the front wall would be right here, instead of measuring here from to that corner. Now it's further if I measure there, it's shorter if I go perpendicular to the wall. So from A to B is shorter than A to C. All right, construction. I think if you turn the page, you will find a couple construction spaces. I don't think yours sets up exactly like I put up there. You have more of a horizontal line, a point above it. Okay, I'll set it up on the board here like what you did, or like what's on your notes. Make sense? Basically the same construction, but that starting point is in a different location. Then we did the perpendicular bisector earlier, so we've got 3 ways to come up with perpendiculars right now. So I think you will need some construction tools for your assignment. So some of you said you have some in your locker. Well, don't take another set then. That's what I'm running out. Don't take another, not bringing them back. But you will need some for your assignment. All right, then the last part for the lesson is there are 3 theorems. And then we'll do some practice problems related to those 3 theorems. I think as you do the theorems, I have a feeling that the first thing you look at is the pictures. You haven't even read the theorem, am I right? Some of you are taking notes, you're just drawing the picture. You have no idea what the theorem says. So you need to focus more on what the theorem's saying. Maybe I shouldn't even have the hypothesis or conclusion up there. Make you read through it and draw it. So what is being drawn on the hypothesis? Well, that's the if part. So if 2 intersecting lines form a linear pair of congruent angles, that's what the hypothesis picture is. We have 2 intersecting lines. The linear pair of angles, in this case, are congruent. Why do you need a hypothesis? Well, to use this theorem, you have to have that stuff. Now, some of you are wondering what to use in a proof. How do you come up with what theorem it is? Well, you've got to think about the problem and say, oh, okay, I have 2 intersecting lines and those adjacent angles are congruent. I could use congruent linear pair theorem. So you have to think about the hypothesis to use the theorem, and what kind of thing do you support is what the conclusion's telling you. So in this case, you can support perpendicular lines. So the hypothesis and conclusion is this is what you have to use the theorem, and this is what you are supporting because of the theorem. So if you're doing a proof, if you're trying to support something like L parallel to M, it might be this theorem. You'd have to see if you have what the hypothesis tells you is needed though. So before you go to the next one, let's focus on understanding that first one, okay? So don't look at the next one yet. I should cover it. So if you have adjacent angles, why would this end up perpendicular? Let's reason through. Okay, linear pair. Tell me something about linear pair of angles that we've studied previously. Melissa? They're supplementary, which means they add up to 180. Okay, so these two angles have to add up to 180. In this theorem, they're saying they're also congruent, which means they're the same. So if they're the same and they add up to 180, we already know they're a linear pair. They're congruent and they add up to 180. How big would they be? They'd be 90 and 90, which means they're right angles. And right angles would mean perpendicular lines. It's not that the lines are right angles. The lines are perpendicular because there's right angles. So does this theorem make sense? If you have this situation where those two adjacent angles making a linear pair are congruent, you're always going to have perpendicular lines. If it makes sense, maybe you'll remember it better. I got this name from the basic geometry book, but they named it that in their textbook. Your book didn't have a name for it. Okay, next one, perpendicular transversal theorem. Let's think what this picture is. It says in a plane, so this is all in one flat surface, it's not three-dimensional. If a transversal is perpendicular to one of two parallel lines. So you gotta have a lot for this one. You've gotta have parallel lines. Miguel, are you listening? You've gotta have parallel lines. You've gotta have a transversal perpendicular to one of them. So I think I'm going to write a few things. I have to have n parallel to m, or to p, and I have to have n perpendicular to q to use this theorem. And then according to the theorem, q is perpendicular to p. That's what? That's the hypothesis. The conclusion, I didn't draw in a picture. You don't want to put the conclusion on the hypothesis picture. But now can we reason through why that works? What are some things we've studied that would help us understand why this works? Got some ideas?
Because
N and P are congruent.
Parallel.
Okay, N and P are parallel. Keep going. Which means, okay, 90-degree angle there.
Since it's perpendicular to n,
Okay, I need a theorem or something to help me. Okay, is everybody on the right track? We've got parallel lines, cut by a transversal. This angle's 90. Come up with another angle for me. Look back in our notes. You have some more theorems in this chapter that had parallel lines cut by a transversal. Maybe even the name of them is coming to your mind. Parallel lines cut by a transversal. What theorems or postulates am I thinking of? Things like, and the converse, is it two parallel lines cut by a transversal?
two coplanar.
Just coplanar, so that's not what we want. The corresponding angle postulate, does that have two parallel lines cut by a transversal?
Yeah.
Okay, those are the right ones, it's not the converses. So if we used corresponding angles postulate, wouldn't we be able to support this angle right here being 90 degrees? That fits the theorem. And if this is 90 degrees, wouldn't we be calling lines Q and P perpendicular? So we can really reason through this one by knowing the corresponding angle postulate. It's really just a special situation of that. Okay, the last one, dual perpendiculars theorem. If two coplanar lines, so again, they're in the same plane, are perpendicular to the same line. Okay, it doesn't say they have to be parallel. Two coplanar lines perpendicular to the same line. So look at our picture. We have T and R perpendicular. So R is perpendicular to T. Also S is perpendicular to T. Two lines perpendicular to the same line. That's the hypothesis. What can we conclude? Then the lines, R and S, are parallel to each other. Now, how could we reason through that based upon something that we've already studied this chapter? Well, kind of reverses. If this angle's 90 and this angle's 90, those are corresponding angles. So what in your notes from this chapter says, if the corresponding angles are congruent, then the lines are parallel? Erica? Yes, converse of the corresponding angle postulate. So again, a special case of it because of the 90s. All right, so hopefully you'll think about those. And you'll probably need to work on studying those a little bit more before Wednesday's test because the last section you don't get as many days to practice. Okay, here is an example of one of those current theorems. So look at those three new theorems. Let's figure out which one this is a real life example of. We have a carpenter's square that forms a right angle. It's this device. The carpenter places the square so one side's parallel to the edge of the board, draws a line along the other side, slides it, draws a second line. So what theorem supports that the two lines that were drawn end up parallel? Dual perpendicular theorem? Does that say, I'll read it, I guess.
If two coplanar lines are perpendicular to the same line, then two lines are parallel to each other.
Right, so the lines that were drawn were both perpendicular to the same edge, same line. So correct, that is the correct theorem. Perpendicular, or dual perpendiculars theorem. So there can be real life examples. Let's do a couple proofs. Now, you're not going to be doing proofs from scratch yet on this test. Next chapter, yes. Okay. So I'll give you parts of this and see if you can help me get the others. Okay, write it down. You've got space there beside your constructions. There's going to be two proofs. So use half of it for this one and find another space for the next one. Okay, we're trying to do a couple proofs that use these last two theorems, or these last theorems. I guess there's three theorems. Write a two-column proof. And I'm going to lead you and see if you can help fill in the missing parts. Okay, got the picture? Mark it the correct way. Now I'm going to first say R is parallel to S. Where did I get that?
Good.
Okay, given. And do you have it marked on your picture? Okay, parallel lines. Let's see, we had some theorems. Let's see if you can come up with something using the corresponding angle postulate. Okay, so use what we already said. This line is parallel to this one. Pick out a transversal. What kind of thing can you conclude from the corresponding angle postulate? I'm giving you the reason. See if you can come up with a statement to support. What can we support about that picture based on the corresponding angle postulate? Read that postulate. Flip to it. If two parallel lines are cut by a transversal, then so can you pick out a pair of corresponding angles in that diagram and tell me about them being congruent? Okay, what do you want to say about angle 3 and angle 2? Okay, does the theorem say equal? Congruent. Okay, congruent. So he wants to say angle 3 is congruent. I'm going to put angle 2 first. Angle 2, you'll see why in just a little bit. Angle 2 congruent to angle 3. So basically I agreed with Tina. Corresponding angles are congruent. Okay, I'm going to now come up with angle 1 is congruent to angle 2. Where did I get that? Oh, given. Okay, so let me mark, right now I have, oh wait, no, not yet. Okay, what I want you to do next is a transitive property of congruence. Look at those last two statements. What's the transitive property of congruence going to support? Think about the train, the engine, the cars, the caboose. Yeah. Angle 1 congruent to angle 3. That's what I was going to mark up here just a little bit ago. We've got angle 1 congruent to angle 3 right now. Look at your new theorems. Look at what you drew in the hypothesis. There's one that the picture is kind of like what we got. There's a little bit more to what's up here, but isn't there one where those two angles are congruent? Congruent linear pair theorem. What's the type of conclusion? What can we conclude from that theorem?
Oh.
Look at the conclusion and relate it to this picture. Something about perpendicular. Which ones are perpendicular? T and R. Or R and T? So we can do R perpendicular to T because of what reason? Congruent linear pair theorem. And we proved what we were supposed to. That would make sense? Okay, one more proof. The rest of it's on the board still. And I think when I made up the solution for the slideshow, I just put all the given together, so that's one line shorter. But I think it's easier to follow what we did on the board. Okay, on this one, I have given you the statements, and you're going to give me the reasons. So again, let's look at the picture. It's arranged a little bit differently. Different information to start with. Let's see if you can support the. So Gail, are you having an example?
Yeah, I figured out.
Okay, angle 1 congruent to angle 2. I'm going to mark that on the picture. Angle 1 congruent to angle 2 was given. So if 1 are congruent to 2, does that make this line parallel to this one? Those lines have to be parallel since 1 and 2 are congruent. What kind of things support lines of parallel? Look through your notes. What are some theorems that have the conclusion lines that are parallel? What kind of ideas? What concludes then lines are parallel? Find the right theorem. You're headed the right way. Morning, Kay. Got an idea? Looking for things where the conclusion is lines are parallel. There was a new one today. Did you want to have an idea, Morgan? Dual perpendiculars theorem, what's the if part say on that? Okay, do we have two lines perpendicular? We just have congruent right now. So nope, I do see that there is one perpendicular, but it said both perpendicular. So we don't have both. Can't use that one.
Perpendicular transversal.
Let's see, what's the hypothesis of the perpendicular transversal
If
theorem?
a plane is a transversal, it's perpendicular to one of the two parallel lines, then it is perpendicular to the other line.
Okay, so a transversal, well, what's the conclusion?
Then it is perpendicular.
Right now, I'm trying to come up with
Oh.
parallels, so nope, that one's not gonna work. Okay, corresponding angle postulate, what's the hypothesis?
Two parallel lines are cut by transversal.
Okay, do we have two parallel lines right now? Cut by a transversal? Do we have parallel lines, or are we trying to conclude parallel lines?
I don't know.
We're trying to conclude them. We're close, but not the right one yet.
Is it the converse?
It's the converse of corresponding angle postulate. Because we have corresponding angles congruent. Okay, then you can conclude the lines are parallel. So, converse of the corresponding angle postulate gets those lines parallel. Okay, so they are parallel. Now I'm going to say P is perpendicular to Q, given. Now we should be able to support P perpendicular to R. Is this the dual perpendiculars theorem? What's the conclusion on dual perpendiculars?
The two lines are parallel.
No, we don't want parallel. What are my other choices?
Perpendicular transversal theorem.
Perpendicular transversal theorem, read the if part of that. Let's see if that's what we have.
If the transversal is perpendicular to one of two parallel lines.
Okay. So do we have parallel lines?
Yes.
Yeah. Do we have the transversal perpendicular to one of them?
Yeah.
Yes, that fits. What's the conclusion? Then,
Then it is perpendicular to the other line.
okay, so then R is perpendicular to P. Yes. What was the name of it?
Perpendicular transversal theorem.
Correct. Is that helping to see what I'm thinking of when I'm doing the step-by-step proof? You really have to know the hypothesis better than you probably know it right now. That's why I sent out that remind, study your Quizlet flashcards, study those theorems. You've got to know what the hypothesis is so that you know if you have that, then you can use that theorem. And if you don't, you can't. So you got to know the hypothesis conclusion better than just writing them down. All right, so that's what I thought we needed to work on today. I'm hoping we spent enough time on equations